So we are reached to new section that are laws of thermodynamics and reversibility. So as you have studied, you know that work and heat mutually transferable. That means heat can be converted into work or work can be converted into heat. That is possible. You see here at the top of the figure there is a spark plug which is lighting and combustion process is taken place. Then high pressure gases push the pistons down. That is one example for heat or heat is converted into work. That means energy with high pressure gases after the combustion pushes piston down. In other words, heat converted into work. So from this example, now we are going to study laws of thermodynamics. Associated with processes which while interacting work and heat. Again, if we say, now we are going to study the laws of thermodynamics while we deal with processes that are taken place interacting work and heat. First law of thermodynamics. Heat and work are mutually convertible, as we know from the first slide. That means work can be transferred into heat or heat can be transferred into work. Both are mutually convertible and transferable. So then what is first law of thermodynamics? As a definition, when a closed system undergoes a cycle, net heat transfer is equal to the net work transfer. But heat and work taken in kilojoule. So, shall we think about this with the knowledge gained through what we have learned up to now? So, what we have learned? So, the processes are taken place from state changes. Now, here you can observe a cycle. State 1 converted into state 2, again reach to state 1, completing a cycle. But within a cycle. So that means once this cycle is taken place, you can observe heat can transfer as well as work can transfer. So then first law of thermodynamics says that once this process is taken place within a system, while within a closed system, while that means your work employed is not flowing anywhere, the work employed remain inside, processes are taken place with a cycle. So then within this system, within this closed system, with a cycle, you can say net heat transfer is equal to net work transfer, while these quantities are taken in kilojoule. Otherwise, heat transfer is proportional to work transfer. That is what first law of is expressed. So, finally, simply what you should remember is once the definition, when a closed system undergoes a cycle, net heat transfer is equal to the net work transfer taken in kilojoule. Then what is your practical law, industrial law? The conceptual idea. You have a closed system as shown in the figure. So the cyclic process is taken place between 1 and 2. Then net heat transfer is equal to net work transfer taken in kilojoule. I think it is understood. Now we already studied first law of thermodynamics. We see it is again. When a closed system undergoes a cycle, net heat transfer is equal to the net work transfer. Heat and work measured in kilojoule. I think you remember forever the same figure what you have studied earlier. So cyclic process is taken place within the system, within your closed system, and the sigma W is equal to sigma Q in kilojoule. That is your first law. In other words, this is somewhat similar to the law of energy conservation that you have studied in advanced level. Energy cannot be created or destroyed. In other words, energy can neither be created nor destroyed. It is compatible with energy conservation. Now you should not remember first law forever and ever. Now we are going to study important thing, which is a corollary of first law. Corollary of first law. So when heat is added into a system, it can be considered as given in following. What is it? First thing, if you add heat into your system, your closed system, what happened to the system inside? So one thing, the internal energy can be changed within the system. It is one thing which could be happen. The next thing, once you supplied heat, that heat can be converted into work, as well as the example you have seen very first, the engine like piston moving with the combustion, right? Then what you should remember, if you supply heat into a system, that heat can be remained within the system as internal energy, or that supplied heat energy can store in the system as internal energy, or that heat can be converted into work. So the heat into work, you have seen an example. But what is an example for heat converted into change in internal energy? What is the example? Example is, once you supplied heat into a system, the work employed inside the system can heat it up. The temperature can rise, increasing kinetic energy inside the system, but without flowing. So then, internal energy is a part of the energy that can be identified with the property of temperature. What is that? You can identify another entity or quantity which is independent of other things, which is internal energy as a different property. So then you can derive another equation, which is the heat transfer is equal to the change in internal energy plus work done. What it says? Simply it is like that. Example, you have a process taken place in a particular system with your working fluid, then you supply heat as told. What happened to this heat supplied, or the quantity? Then part is going to increase its internal energy as du. The balance, the rest of the energy can convert or transfer into work. It simply says dq is equal to du plus dw. So then you should remember this equation forever, which could be derived from first law. I will give this derivation. It is very simple for an assignment. The guidance will be given if it is required. I would like to express first law again in a different set of using different set of words. Why? So what you have studied, you should apply. Then you should have the physical understanding of the law and how it interacts with industrial scenarios. Okay, we'll see. Then you have the system and you have the surrounding. Okay, so therefore, shall you read this? During an interaction between a system and its surrounding, the amount of energy gained by the system is equal to the amount of heat or amount of energy lost by the surroundings. It is another way of expressing your first law. What it says? Energy lost by the surrounding. What is it? Energy lost by the surrounding means outside. That means you have the supplied energy. Another word, heat supplied to the system is identified as heat lost by the surrounding. And heat gained by the system is, what is it? Heat gained by the system is your internal energy increased due to supplied heat plus the work which is converted. Okay, now it is very clear this form of definition. So also you know that this obey with energy conservation, which is energy can neither be created nor destroyed. I think we have a clear understanding of first law of thermodynamics and its applications. Then we can move forward. Now we reach to important definition, which is related to the practical scenarios. Reversible processes and irreversible processes. So first, as we know, what is thermodynamic process? As you studied, the process means is the particular mean of causing state changes. So that is the process. Then thermodynamic process could be understood as system change its state from one equilibrium state to another equilibrium state. So that is what you should understand, as a thermodynamic process. That means simply one equilibrium state to another equilibrium state. Connection is through a thermodynamic process. Then we'll move on to reversible process. Very important. Process is consisted with each intermediate states that are at equilibrium states. What do you mean by that? Process is consisted with each intermediate state that are at equilibrium states. It simply says, if you select a process between two states, right, that particular process should pass through infinite number of states within that slot or within that portion state. That means you have infinitesimally small states in between state 1 and state 2. So each states are considered as equilibrium states. Indirectly, it says that the process can be reversed along the same path. Why? The intermediate states or intermediate equilibrium states are all are equilibrium. All are at equilibrium. So therefore you can reverse through each and every points. So therefore you should simply understand that reversible processes are such processes that could be reversed along the same path. Due to these infinitesimally equilibrium places within the entire span. Okay, now it is very clear. Reversible processes are ideal processes, theoretical processes, which cannot be seen in the actual scenarios. Oh, actually. So we'll see then what are those actual processes, real world processes that are irreversible process. Once a process is taken place between two states that could not be reversed along the same path, such processes are called irreversible processes. Most of the processes in industry, everywhere in the real world, can be understood as irreversible processes. All are irreversible, that cannot be reversed along the same path. Shall we read this? Intermediate states are not at equilibrium states, and therefore process cannot be reversed along the same path of the process followed. So then I say you have proper meaning or proper understanding about thermodynamic processes, reversible processes, and irreversible processes. Finally, reversible processes are such processes that could be reversed along the same path, and irreversible processes are such processes that could not be reversed along the same path. That means reversible processes are ideal processes and irreversible processes are real processes. Oh, very happy. We have finished the session. Now we have reached to summary. So throughout this lesson, I'm not going to read. You should know these are the important things and summary. You should do yourself. Okay, you have to take care of yourself, adhere to the measures taken from the governments to reduce vulnerability with this serious virus, spreading virus, COVID-19, until the mitigation is completed. Take care. Important thing, you should remember what you have studied. Take care. Have a good day.